Adapting traditional penetration testing for generative artificial intelligence, Gen AI systems, requires a deep understanding of the unique challenges these technologies present, including data poisoning, model inversion, prompt injection, and adversarial attacks designed to manipulate AI outputs. Unlike conventional systems, AI models are dynamic, learning from new data and potentially altering their behavior over time, which demands continuous and adaptive testing approaches. Cybersecurity professionals must evolve existing methodologies to include AI-specific threat modeling, specialized reconnaissance for training data and model architecture, and techniques to evaluate the integrity, confidentiality, and availability of AI-driven processes. Effective assessments should simulate real-world AI exploitation scenarios, identify vulnerabilities in both the model and its supporting infrastructure, and recommend countermeasures to mitigate risks. Adversarial prompt injection testing is typically conducted during Phase 3, exploitation, where penetration testers actively leverage identified vulnerabilities to determine the extent of potential compromise. In the context of generative AI systems, this involves crafting and delivering malicious or manipulative prompts designed to bypass safeguards, extract sensitive information, or alter system behavior in unintended ways. By simulating realistic attack scenarios, testers can evaluate how the AI model responds under adversarial conditions, identifying weaknesses in input validation, context handling, and output filtering. This process not only measures the system's resilience against prompt-based manipulation, but also provides actionable insights for improving defenses. In the planning and reconnaissance phases of penetration testing, traditional methods focus on defining test boundaries, setting engagement rules, and gathering intelligence through open-source intelligence, OSINT, to identify potential targets and weaknesses. When assessing generative artificial intelligence, Gen AI systems, however, these steps must be expanded to include identifying AI-specific system boundaries, mapping data flows between components, and analyzing how prompts are processed and handled by the model. Scanning in traditional environments typically involves network mapping, port enumeration, and vulnerability scanning to uncover exploitable services. In Gen AI-focused testing, this stage extends to enumerating model application programming interfaces, APIs, reviewing training datasets and documentation, and analyzing integration points with other systems to understand how data pathways could be exploited. This deeper AI-specific reconnaissance ensures a more accurate identification of vulnerabilities, leading to more effective and targeted exploitation strategies later in the engagement. In generative AI exploitation, specialized techniques such as prompt injection attacks and jailbreaking are central to bypassing built-in safety measures and manipulating model outputs beyond their intended scope. These methods can be used to coerce the AI into revealing restricted information, executing unintended tasks, or producing harmful content. Data extraction through inference attacks allows adversaries to deduce sensitive training data or proprietary information, while model poisoning manipulates the AI's learning process to embed malicious behavior or biases. Post-exploitation efforts focus on maintaining persistent access to the compromised AI environment, pivoting to connected systems or APIs, and exploring secondary attack surfaces. Unlike traditional exploitation that targets purely technical flaws, Gen AI exploitation also requires assessing vulnerabilities in the model's logic, contextual understanding, and decision-making processes. This approach ensures a comprehensive evaluation of both the technical and cognitive weaknesses of AI systems, enabling more effective defense strategies against evolving threats. In the reporting phase of a penetration test, the goal is to deliver a clear and comprehensive account of the assessment's outcomes, tailored for both executive and technical audiences. The executive summary should highlight the most critical findings, their potential business impact, and an overview of the system's overall security posture. Detailed technical documentation must follow, outlining each vulnerability with in-depth descriptions, proof of concept evidence, and associated risk assessment metrics to quantify severity. Actionable remediation steps should be provided, prioritizing fixes that address the most urgent risks first. For generative AI systems, special attention must be given to AI-specific mitigations, such as implementing prompt security controls, applying model guardrails, monitoring for adversarial inputs, and securing training data. Conducting a penetration test on AI chatbots requires a structured approach to uncover and address security weaknesses unique to conversational AI systems. The process begins with enumeration and reconnaissance, where testers gather detailed information about the chatbot's architecture, data flows, API endpoints, and integration points to understand its operational environment. This is followed by targeted exploitation attempts, such as privilege escalation, to determine whether unauthorized access to sensitive data or system functions is possible. Testers then proceed to identify and document vulnerabilities, including issues like prompt injection, inadequate input validation, or insecure backend connections. Each finding should be validated with proof of concept demonstrations and analyzed for potential impact. Finally, vulnerabilities are reported with clear technical details, risk ratings, and actionable remediation steps tailored to AI systems. Understanding and applying these processes is critical for strengthening chatbot security, ensuring resilience against evolving AI-specific threats.